So we will now learn about something called Montgomery's template method. Which is another way of finding observers. So how did we find the observer in the previous section? So in the previous video, we learned about this approximate version of Posat's conjecture that give us the square of a Hamilton cycle. And we know that for each vertex, there are like omega of n to the 5 observing tuple. So like observing 5 tuple. And then how you find the observer, you take randomly select each tuple with the probability omega of n to the negative 4 that yields linearly many tuples. And if ensure that there are these linearly many tuples, and then each vertex is, it is observed by linearly many of them. So this is your observer, and then like by connecting it, you get the path, square path that you wanted. Okay. So the key for this to work is that there are like omega of n to the 5 many observing tuples. But what if this is not true? What if you don't have enough, observer for each vertex? Such a case, there is still way to find observer. But in such a case, still, we need to be able to find the linearly many disjoint tuple for each vertex. For one specific vertex, let's say you can still find the linearly many tuple. Maybe not just vertex, but small set. For this specific small set, then you can find linearly many of them. And somehow you want to find the linearly many of them that contains many observers for each one of them. But that's the ideal situation. Okay, so yeah, maybe I will get into the examples of how we can actually deal with this case. So consider the following theorem. This is theorem by Low and Sharifzadeh and Molla in 2016 that for epsilon positive, there exists delta. Okay, let me just again write in this way. So, and 3 divides n is divisible by 3. And if this G is an n-vertex graph with minimum degree half plus epsilon times n, and its independence number is more than delta n, then this G contains K3 factor. So Heinrich-Emery theorem, or this specific theorem for K3 factor is Korody-Heinrich theorem, says that the minimum degree bigger than 1, 3, and then you have like a K3 factor. And this is type because what? You consider the complete three-part type graph. Which is slightly unbalanced. So let's say you have n over 3, n over 3, and n over 3, but say plus 1, minus 1 here. Then, every time you take a triangle, it uses one vertex from each. And then at the end, some vertex, two vertex here, one vertex here are left uncovered. And then this has a slightly less minimum degree. So this shows that this theorem is tight. So you cannot improve it anymore. But if you see this Dirac type problem, then most of the cases, the extremal example come from this complete multiple type graph. Slightly unbalanced complete multiple type graph. So natural question is that if you know that your graph is not close to this, if your graph is far from this, then can we do better? So we know this condition implies K3 factor and then you cannot improve it. But if you add some additional condition that your graph is not so close to this, then can you improve it? So that's natural question. And here we have this complete multiple type graph. We have this large independence of size n over 3. So we can consider the case that if your graph has independence number much smaller, then can you improve this? And this theorem says that it is possible. So this is highly related to something called the Ramsey-Dirac theorem. Ramsey-Dirac theory. So similarly as like this, so Dirac theorem said that Dirac theorem states that if you have a certain number of edges is above certain threshold, and you can find some KK, copy of KK. Again, the extremal example is complete multiple type graph. So you ask a similar question. What if you know that your graph has 0 of n independent number? Your graph has small independent number, then can you get a better bound on the number of edges? So this is called Ramsey-Dirac because in Ramsey theory, what do? You forbid large independent number and then try to find clique. So that's same as a Ramsey number, KTT, roughly. And you ask the Dirac theorem in the context of Ramsey. So you forbid the large independent set, and how many edges do you need to find a certain copy H? So that's Ramsey-Dirac theory. And then this above one is dealing with Dirac type question in, again, Ramsey context. So Ramsey-Dirac or Dirac-Ramsey theory, you can call it. So Dirac theorem type is giving minimum degree, you want to find the spanning structure. In Dirac theorem, giving the bounds on the number of edges, you want to find the one structure. Okay, so for this Ramsey-Dirac theory, there are like survey by Simonovich and Schloss in 2001. And also there are, lots of other reference regarding that. And this Ramsey-Dirac type theory was not really considered before. And last decade, it had been considered, quite a lot. So now we want to prove this theorem. But now, what? We want to use observer. And here, observing one vertex is impossible because here you have to have a triangle factor, and then together with this, you also have to have triangle factor. This is simply not possible. One of them is not divisible by 3. So for each triple, you should, consider observer. So we want to find the observer in the say that for a set S of size 3, we want to find the set X such that both G bracket X and G bracket X union of S contains a triangle factor. So that's observer X for that observed the set S. Then what? Ideally, if we want to proceed as the previous section, we want to find for fixed F. We want to find the X of size, say, 3X. How many of them? Say, at least, so n to the 3X many choices of X which has size 3X. However, we consider the following example showing that this is not possible. What you do is you take B1 of the size half minus epsilon n and B2 and then B3 of size quarter plus epsilon over 2n. So altogether it's n vertices. And we put the complete bipartite graph here and here. And between here, we put the 2 epsilon and regular bipartite graph. Then what? Then its minimum degree is at least like half plus epsilon times n. And yeah, the problem now is that it has still large independent set. So what we do is we put some random graph. We put the random graph G, Ni, log square Ni over Ni in its Pi, where this Ni is the size. Then what we know? Then we can check that its independence number is like small, little of n. Moreover, I mean, it's like, to be more specific, big of n over log n. And like, also we know that the maximum degree of G is roughly like 10n log square n inside each I. So with high probability, these hold. Okay, then what? You choose S as 3 vertices here, which are independent set. So S is an independent set in B2 union B3. And how many observers are there? So if you have X, which is observer, and then you have S here, then what? This must contain X triangle. And this must contain X plus 1 triangle. Small x. Right? But what do we know? Every triangle in G is either containing I mean, one vertex, what? How does it look? One vertex from each B1, B2, B3, or it's like, okay, let's write it this way. It either contains one vertex from B1, or it contains an edge of GB2 or GB3. Let's try GI. Exactly. So exactly one vertex from B1, or it contains the edge from this. And what? If this X contains exactly one vertex from B1, the first case, so all the triangles, so this has this triangle vector, right? If all of them is the first case, then it's not possible. So because last one, we have like two vertex here, one, and they are independent set. So altogether, you have to have again triangle, 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 and at least one of them has to be in the latter case. So okay, let me write it this way. At least one of these x plus 1 triangle must use on H in GVI. Because otherwise, I mean, altogether, it should use the same number of vertices from here and here and here, but the S already have like two vertex here. So you can check that this is true. So in that case, what? We know that this, I mean, so N is not here, and it should not be here. So this is true, right? So when you choose this vertex X, at some point you have to choose a vertex so that it forms an edge inside of GI with the previous vertex. That means the number of choices of this X is at most big O of n to the X minus 1 times log square because of this condition. So you choose one vertex by one vertex in this X. For one vertex, there are n choices. One vertex, there are at most n choices. At some point, because of this vertex must form an edge with one of the previously selected vertex. It may be in X or it may be in S. It may be in here or here. And at that time, the number of choices is restricted to this times like X maybe. So one of the X vertices previously. So altogether you have this. So this is little rho of X to the N to the X. Sorry, 3X. So if you do the same approach as before, you just randomly choose it so that you obtain linearly many observers for one of each of them, then it would fail. Because for this S, the number of observers for it is too small. Then how do we overcome this? There is this lemma by Montgomery, which is useful. Let's say M is sufficiently large number, then there exists a bipartite graph H with bipartition X union Y, comma G. So you have like X, Y, G, with X has size 2m, Y has size 2m, and G has size 3m, and the maximum degree of H is m of 40. So small, such that for any subset X prime of X with the size exactly m, the graph H, you just take this X prime and Y and G, this has a perfect matching. So no matter what X prime of size exactly m you take, so together with this, you can find the perfect matching between here and here. So this is the Montgomery's lemma. Maybe we will just briefly discuss about how it can be proved. You take X and then you take take G prime, which has size 2m, and you take you add a perfect matching and then another perfect matching. So you take 20 random perfect matching. You add them. And then you duplicate this into Y. And you duplicate half of them into A double prime and then G double prime. And this is G. And that's your graph. And then what you do is you show that the neighborhood of A is at least 2 times A for all a small set, or a small set of this subset of G prime with size n most say m over 2. So you can show this. And yeah, with high probability, you can show that. And then you can show that for any of size bigger than m over 2, you show that there is edge between them. So because you constructed your graph in random way, you can show that with positive probability, both of them happen. Once you know both of these, then you can actually check the Hall's condition, for arbitrary x prime, and you take this, and then you check the Hall's condition actually holds between this and here, so that you can find the guarantee of perfect matching that you want. So that's roughly how you prove this. But this lemma is so useful. So no matter what vertices you might use in the remaining one, you can find the perfect matching here. So that's kind of observing. So what you do is you find this, and then you find the approximate structure here, and then you use your approximate structure to use some of the vertices here, so that the only small number remain here. And then here you use this perfect matching to finish your approximate structure into, optimal one. And then while you're doing that, this maximum degree bounded condition is crucial. And then because of that, this is useful to construct an observer. We will see soon. Okay, let's collect some lemma as well. So this is a lemma which is useful for finding approximate structure. Let's say your minimum degree is at least half plus epsilon times n. and your independence number is small, then it contains at least 6 minus eta n, say, not 6, sorry, 1 over 3 vertex disjoint copies of triangle. So proof is, not difficult. What you do is you apply regularity lemma. Then you find the partition. And in reduced graph R, you have a, minimum degree R plus epsilon over 2 times R. Then you find the perfect matching. And B0 is here. And you apply the regularity lemma with, say, epsilon prime. If epsilon prime is between delta and like eta here. So these are epsilon prime regular, and B0 is epsilon prime. And in each regular partition, what? You choose one vertex here, and then you take each neighborhood. And this neighborhood has like a size at least some small number, say D, n over R, but the delta is much smaller than D over R. Then there you can find an H because you have this condition. All the independent sets are small. That means that if you take this large set, it must contain an H. So you take this and then you put it out. And then next time you choose this one vertex, and then you repeat. You have a neighborhood and you choose an H, then you take a triangle and you put it out. You can do that until like this part is bigger than square root of epsilon prime n over R. It is still like a smaller set, but this is still square root of epsilon prime regular. Then you can keep do that. You do that until only very small fraction remain. And then you do that for each one of them, and then the remaining parts is like small, less, but bigger than epsilon prime, but smaller than eta fraction, and then this fraction is also small. So total, you can cover everything except the eta fraction, so you get what you want. Okay, I will not write down in rigorous way, but you can see this lemma. And another lemma is that this guarantees that for each f, you can find linearly many x that observes s. So again, your minimum degree is bigger than half plus epsilon n, and your independence number is smaller than delta n. And for every subset S of die 3, there exists the collection of the epsilon n over 10 vertex disjoint. That's the T1 to T epsilon n over 10 of size 9, such that for each I, both GTI and G bracket TI union F have a K3 factor. So each of them are observable for this set S. How do you prove it? Let's say S is 3 vertices, U1, U2, U3. And assume that you have already found T1 to Tj. So you together, it's like J is smaller than epsilon n over 10. So this set has size, what? At most 9 epsilon n over 10. And in the remaining one, the minimum degree of G is still half plus epsilon over 10 and G prime. So G prime is G minus the U. Not U, let's say T. Okay, so still have lots of, degree. Then what? Out of here, you should be able to find the triangle B1, B2, B3. Why? Here, deleting 3 vertices still degree is more than half. That means you choose any 2 adjacent vertices, then they have a common neighbor. So you have this. And for these 2, you consider their common neighborhood. And their common neighborhood has size at least like epsilon 10n. And because of the this has size at least epsilon over 10, and because we have this condition that the independent set, all independent set has size smaller than delta and delta is small, so this was contained on H. So what you do is you find this, and you do that for each one of them. Then now we want to argue that this is our Tj plus 1, next one. Why? So here, if you take E3 triangle, then that's a triangle vector in G bracket Tj plus 1. Okay? But if you take, say, this triangle, and this triangle, and this triangle, then that's again triangle vector in G of T J plus 1 union with F. So that satisfies what we want. So we can add this Tj plus 1, which consists of the V1, V2, V3, and these 2 vertices, these 2 vertices, these 2 vertices, and you have. You can repeat this until, where you have this many, and then they are vertex disjoint. So that proves this lemma. Now we have this lemma. So now we can prove this Ramsey-Dirac type statement for triangle vector. So for our convenience, let's say you introduce eta and beta satisfying this hierarchy, and let M be the beta n, where 3 divides this n. You choose this beta so that the beta n is actually the integer, which is divisible by 3. That's no problem. And what we choose random step x of size 2m. Then by Chernow bound, we No, with high probability, we know that every vertex has like 1 plus epsilon over 2m neighbors here for every p. So we know this. So you have x, and then every vertex tends around a bit over than half neighbors in there. And then what we do is we take the arbitrary pairwise disjoint sets y, C1 to C3m with y has size 2m, and each gi has size 2. So you have x, and then you have y, and so C1, C2, C3m. What we are doing, now we are building our observer. And then how do we want to build this observer? We use the Montgomery's template method. By Montgomery's lemma, then we have a bipartite graph H with parts say x star, y star, c star, both sides like 2m, and 3m. And we consider bijection theta from like x star to x, y star to y, and then this g star to 3m. And you have this h. And then based on how this looks like, here we will construct something. What do we do? So what do we do? So for each h, say AB in E of H, say here A, you have B, we consider the set pi A union with G pi B. So let's say you are here, then what? This maps to some vertex here. This maps to some number here that correspond to these two vertex. And this is it. So this is the set of size 3. And what we know? And lemma, the previous lemma, says that there are at least epsilon n over 10 vertex disjoint observers T1 to T epsilon n over 10 for this set. And we choose one of them to be TAB for each AB in this H, so that they are all disjoint. It's a collection of pairwise disjoint. So meaning is that if we have edge between this and this, then here, what? We choose one of these things that is your observer. And for, say, another edge, say, between this and this, or let's say between this and this, you add another one here, so that this and this are disjoint. That's possible because every time you do that, what? Indeed, this is possible, as the number of edges in H is almost 400 m. The number of vertices here is 7 m, and then maximum degree is 40, so which is like say much more than epsilon n over 100. So that while you're doing that, the number of vertices you have used is almost epsilon n over 100. But every time you have this many choices, and out of these choices, they are vertex disjoint. At least one of them does not use any vertex from here, so you can add. Then that A is the union of this Y, G1 to G3M, and TAB for AB, all the edges in here, and as well as X. Then, now what? You have this huge graph. Small graph, not huge. Altogether, what? How many vertices are there? Like 7m plus. For each one of them, this consists of 9 vertices. 9 epsilon n over, say, 100. More precisely, 9 times 400 beta n. So altogether, it's like less than 10 to the 4m. Then what happened? This A has a special property. What? For any x prime, which is subset of this, with a side exactly m, x prime union with A contains a K3 factor. Okay, let's say A, this does not contain x. So A is the remaining thing, so this part without x. So this is A, and x is outside. Then we want to say that this holds. Okay, but y, you have what? You have this like x prime, and then y, and you have g, and what? Let's say you have this triangle here. Here, and then let's say you have one more thing. Let's say you have this. And what? In H, so this one come from this H, right? In H, you take a corresponding x prime, and there you have a perfect matching. And that perfect matching actually corresponds to here. Say this one and this one and this one. This edge is not included. And what you do is that for all the ones that's corresponding to the perfect matching edges, you take the triangle vector that includes x and g. And here as well. But for the edges that's not included in the perfect matching, you take the triangle vector that only covers the observer TI, but TAB, not the vertices in XG. Then this is a triangle vector that covers X star and A. So indeed, H contains a perfect matching, say M, that cover all vertices in pi inverse X prime and all vertices in Y and C star. Then we consider the A3 vector in the pi A union with G pi B and TAB for each AB in this matching, like this red one. And K3 vector in TAB for each AB in H that is not in M. So obviously, I mean, some of the vertices here. Okay, so maybe I should have also drawn this. So this belongs to this A, but here what we take this. Even if, I mean, some edges might touches the part of X that's not included in X prime, but this is also fine. So this is altogether A. And this provides a K3 vector. And give me a moment. Okay, so now we have this observer. Okay, now we have this observer. Now what do we do? So this A is covered and then Y is here. Now consider graph G prime, which is G minus X and A. As X union of A is almost like how many we have? 10 to the 4 times M, like 10 to the 4 times beta n, which is small. So G prime still satisfy like this condition where M prime is the number of vertices in G prime. And by the previous approximate K3 vector result, you can find by one of the previous lemma, we can find an almost K3 vector F in G prime that covers all, let's say, eta n vertices. Then now what? You have like X and A, and you have many triangles and very small number of uncovered. Then for each vertex P, for each uncovered vertex P, we consider its neighborhood in F, which have size at least like 1 plus epsilon over 2m, which is bigger than delta n. So we can choose an H in here, forming a triangle containing B. So we repeat this until all vertices in like this are covered. Then what? After this, 2m minus say 2 eta n, which is much bigger than m, vertices are left uncovered. Now what you do is for each uncovered vertex P in this X, we do the same thing. We can do the same process by finding a triangle. Again, it stands more than half. So vertex here sends the more than half neighbor thing here. And assuming we have covered less than half, so still more than m are uncovered, then these conditions said that at least like epsilon and m over 2 vertices are uncovered and the neighbor of B. And there it's again bigger than delta n. So you can find an edge, then you can take a triangle. We do this until at most m vertices are left uncovered. And while n is divisible by 3, and this A is also divisible by 3, so number of uncovered vertices is also divisible by 3. So at some point you do that, you can make sure that exactly m vertices are uncovered. M vertices in X. And let it be X prime. Then what? The property that we ensured here, the star ensure that the G A union A prime contains a triangle vector And this together with the previous triangle F yields a triangle vector in G as desired. So this was the Ramsey-Dirac type theorem for this Korody-Heiner theorem. And we use this Montgomery's template method to construct the corresponding observer to solve this problem. Okay, so that was it for today. And in next video, we will talk about something else. Thank you for listening, and I will see you next time.